Hello everyone. So what I want to talk about in this video is probably the most important theorem in your first year of calculus, which is the fundamental theorem of calculus. Now we've already seen in the previous semester what I call the fundamental theorem of calculus light, but now I want to study the full fundamental theorem of calculus in all its glory. But let's start by reviewing what we already know. So we know what the definition of a derivative is, so it calculates the instantaneous rate of change of a function, and it's given in terms of the limit of the difference quotient. We also know what the definition of a definite integral is, which calculates the net area under the curve. It's also given as a limit, but at this time of the Riemann sum. Alright, and then I've already introduced what I call the fundamental theorem of calculus light, which was the statement that if you pick any function which is continuous over an interval, and any antiderivative capital F of the function, so this is a function capital F such that its derivative gives you back the original function, then the integral, the definite integral of the function f of x is equal to the difference in the antiderivative at the endpoints of my integrals. Now the reason why I introduced that before talking about the full fundamental theorem of calculus was so that we can start getting used to evaluate integrals, definite integrals using antiderivatives, and by now we've done a lot of calculations like that, so we're very familiar with the process of using this part of the fundamental theorem of calculus to evaluate definite integrals. But I did not prove this thing because I could not, because I didn't have the full setup of the fundamental theorem of calculus. So this is what we want to study in this video. Okay, so to state the fundamental theorem of calculus, I need to study something which looks like that, which is the integral from a to x of f of t dt. So this kind of crazy looking function is actually calculating the net area under the function f of t between the point a and the point x. This is what I need to study to start to state the fundamental theorem of calculus. So my first question is the following. Is this function a function of x or a function of t? It may not seem obvious at first because both t and x appear in the expression here. So let's study just a simple examples to see what's going on. So suppose pick a very simple function. So pick, for example, f of t is equal to t. And let's calculate what that thing looks like. Well, the integral of a to x of f of t, so f of t is t, dt. So what is this? Well, we know by now we're used to using antiderivatives to calculate these things. So this will be t squared over 2, which is antiderivative of t between x and a. So I'll get x squared over 2 minus a squared, x squared over 2 minus a squared over 2 as the result. So this is what I get for this expression here. So is that a function of x or t? Well, this is clearly a function of x. There's no t left, right? And in general, that would always be true. This was just a simple example, but this will always be true. The t here is kind of a dummy variable. I'm integrating over t, so I'm getting rid of the t. All I will have is the expression evaluated at x minus the expression evaluated at a. So generally speaking, this thing is a function of x. So the answer is it is a function of x, and in fact I will call it g of x in the next slide. So let me write this down. G of x is the integral from a to x of f of t dt. What this function is doing geometrically is calculating the net area under the function between the point t equals a and t equals x. Okay, so we know this is a function of x. Now what can we do with that? Well, since it's a function of x, we can certainly calculate its derivative, right? We can take the derivative of g of x, which is the same as taking the derivative of this whole expression. So this is what I'm writing here. But what is this? Well, let's see. Let's just do a simple example again and see what we get. So we're going to pick the same function that we like. So f of t is equal to t. And then let's calculate what this looks like. Well, then what we're calculating is the derivative of the integral from a to x of t dt, which is a derivative. Now this integral we've already evaluated in the previous slide. What we got was x squared over 2 minus a squared over 2. And I want to calculate the derivative of that. Remember that a is a constant. So what will I get? I get first the derivative of the first term, which gives me 2x over 2, minus the derivative of the second term, but this is a constant. So the derivative is 0. So I recover x. But what is x? Well, x is the same thing as my original function, but now as a function of x. Surprise, surprise. So the derivative of the integral f of t dt is actually equal to f of x. So in this particular case, what we got is that d dx of the integral of a of x f of t dt was precisely equal to the original function f of x. All right, now I'm going to tell you right now that this statement here, which I'm going to circle, is actually completely general. This is the first part of the fundamental theorem of calculus. Now, I will not prove it here, but I will do that in class. So for now, you can trust me that this works not only for this simple example, but it works for any function that is continuous over some interval. All right, so this will be the first part of the fundamental theorem of calculus. So now we're ready to state the full fundamental theorem of calculus. And here it is. All right, so pick any function f, which is continuous over some closed interval between a and b. Then the statement is that the derivative of the integral here of the function f of t dt is always equal to the original function. Now this is true for x between, I should have added x between a and b. So this is the first part of the fundamental theorem of calculus, and the second part of the fundamental theorem of calculus is what we already know, which is that the definite integral of f of x dx between a and b is equal to capital F of b minus capital F of a, where f is an arbitrary antiderivative of f. So we've already used that quite a bit to evaluate integrals. What we didn't know was the first part, which is expressed here. Now, what you should get out of this is that what the fundamental theorem of calculus is saying is really that differentiation and integration are inverse processes. Now, what does that mean? Well, if you look at the first part here is saying that if you first integrate a function f of t, then differentiate, you recover the original function. Right? So you integrate and then differentiate, you recover the original function. Now the second part is saying the exact opposite statement. It may not be obvious here, but notice that I could rewrite, because capital F is an arbitrary antiderivative, capital F prime is equal to little f. So I could rewrite the second statement as saying that the integral of capital F prime dx is equal to f of b minus f of a. So what it's really saying here is that if I first differentiate, so I start with capital F, differentiate it, and then integrate, I recover capital F again. So the first part of the fundamental theorem of calculus is saying that if you integrate and then differentiate, you come back to the original function. The second part is saying that if you first differentiate and then integrate, you also come back with the original function. So integrations and differentiation are really inverse processes. All right, so this is beautiful. This is really important theorem. We're going to prove it in class, or at least sketch the proof in class. Now what I'll do in the next video is show you how you can use, so we already know how to use the second part, but I'll show you how you can use the first part to solve problems in calculus.